Okay, well, thank you for inviting me. This was very much work in progress. So Ollie joined this project a few weeks before I came here. So some of you will know Ollie. He did his PhD here. He's now a postdoc and was a junior research fellow at Trinity.
Remains a junior research
fellow. Well, I know he is here. He's taking a sabbatical from that and being a postdoc in CALTECH. We both work with Paula Antoshechkina, who was here for the first workshop in the MELT and the Mantle program. Although he's not directly involved in what I'm going to be talking about, or the new work I'm going to be talking about today, we are very indebted to Mark Giorso. Without being able to use his source code and adapt his models, and really what we do is just the tip of the iceberg, and what Mark does is everything underneath the water and more. So yes, and so yes, today I'm going to be talking about silicate and carbonatite melts, basically melting in the presence of carbon in the mantle, and how we're trying to add this to the pMELTS thermodynamic model. Okay. So this is an outline of the talk. I'm going to start by just saying some background, not assuming that everybody is necessarily familiar with MELT software and the underlying algorithms. So, hi John. An introduction to why we use thermodynamic models, and some of the different models that are out there, and then the MELTS family of algorithms in particular. A little bit general background on how one actually develops these models, as opposed to applying them. And then I'll actually start talking a little bit about melting in the presence of carbon and the extent to which the current MELT models can capture the behavior of melting and mantle melting with carbonate. And then finally, like our progress so far and next steps of calibrating first melts with the carbon dioxide and eventually with a mixed water carbon dioxide fluid. Okay, so why use thermodynamics? When you do petrological experiments, you tend to do these at constant pressure and temperature. Not all experiments, but most of them are. And other measurements like volume and calorimetry, and we need a framework to take those measurements, parameterize them, and then be able to do calculations like predict phase assemblages and at conditions that are of relevance to geological settings. So that might be heat balanced assimilation in a magma chamber. It could be any there are lots of possibilities. We'll come to this. When you use apply a thermodynamic model, as well as just getting the phase assemblages, the melt fraction, for example, and the solid phases, you get their composition, you get potentially information about the density, the heat capacity, the ordering state in phases that have ordering, like the speciation in the melt, the ferrous ratio, like the redox potential. So there's a wealth of information in there that can feed back with other models like geodynamic models and magma chamber cooling models and so on. There are, of course, many alternatives, which might be anything from as simple as melt fraction versus temperature curve, and that might be all you need. Or a fixed bulk composition, like a phase diagram or pseudo section rather, and that may well be plenty for what you need. And often, if you directly parameterize the data, you will actually obviously return the data more accurately, and you will have a simple functional form that is computationally easy. But you don't normally get quite the same wealth of information, and the energetic constraints, and there's a possibility that you might be able to extend or extrapolate with caution a thermodynamic model, for example, to much lower melt fractions or to higher pressures and so on, to bulk compositions that you can't do if you constrain. All right. So yes, as I sort of continues the same theme. When you do a calculation using a thermodynamic model, you get compositions and things that you can actually compare to all the many different types of real data from real rocks that you can compare with. You can use that for models of trace element partitioning, so how that might depend on composition and pressure and temperature. So, and so again, there's a lot of potential there. Okay, and depending on the parameterization, you can model a wide range of bulk compositions, and also open system behavior by alternating between a fully equilibrated step and an open system. So, for example, if you're modeling mantle melting incremental as incremental batch melting, and then extracting the melt, aggregating it, and so on. You can treat the latent heat of melting in a natural way, and get the energy budget, including if you're trying to deal with a heterogeneous source. Okay. So just a brief reminder, what do we actually mean by using a thermodynamic model? The first law, I'm not going to go through all the equations or anything, they're in the textbook somewhere. The first law is essentially a statement of the conservation of energy. The second law is essentially a statement that disorder is increasing, and the entropy of an isolated system, so closed bulk composition, approaches the maximum at equilibrium. And after some manipulation, you can come up with this energy potential. It gives free energy, and in a given step, you expect that gives free energy to either decrease, or if you're actually at a reaction, to be constant. Okay, and then I should say, so yes, this is the Gibbs free energy G, this is the entropy S, temperature, volume, pressure. There are other thermodynamic potentials that are suitable for other situations. That was for constant pressure and temperature, which, as we've mentioned, is suitable for experiments, phase diagrams, and plenty of other applications. You can derive thermodynamic potentials for other intensive variables. That's like a choice of pressure and volume, and then a choice of temperature, enthalpy, or entropy. So, for example, by Legendre transformation. So, for example, for an isenthalpic, let's say an adiabatic reversible process like mantle upwelling, you can minimize enthalpy. For isochoric process, constant temperature and volume, for example, the crystallization of a melt of a melt inclusion, or evolution of a fluid or melt inclusion, you can minimize Helmholtz energy, where, again, this is entropy, that's F, and S is entropy. For an isenthalpic process, that's an adiabatic irreversible process, which might be suitable for migration of melting cracks and heat balance assimilation, like if you assimilate wall rocks, then you actually maximize entropy. Here's entropy. And at constant pressure, temperature, and bulk composition, we end up with these terms where mu is the chemical potential of the component I, which is the partial molar Gibbs free energy. So if we were for this situation, we have a free energy surface for our initial reservoir. That's usually the liquid in igneous. Well, in the sort of MELTS, original MELTS world, that was the liquid. It could also be, a pseudo solid. That's a sort of best initial guess of what the subsolidus assemblage is, and that's the statement. Oh, it's missing. Okay. If we have another phase and then, at equilibrium, the chemical potentials for a given component in all of the coexisting phases must be equal. And what that amounts to, if you're trying to visualize that, is finding a tangent plane that's tangent to all the equilibrium phases. If a phase has higher Gibbs free energy, then it's undersaturated, and this distance, which I'll show better on a later slide, is in energy units is the degree to which it's undersaturated, and it's called the affinity. So when that's greater than 0, it's undersaturated. When it's equal to 0, it's saturated, it's in equilibrium. And when it's less than 0, it's oversaturated and needs to be added to the assemblage. Okay. So unfortunately, like real phases don't have free energy surfaces and nice balls like this. And in real life, this is molar Gibbs free energy for a binary phase. If it was a simple mechanical mixture of two end members, the free energy would vary linearly. If it's an ideal mixture, you would get this. And if there's some non-ideality, you will get some excess term, which is not necessarily positive. I'm just drawing it as positive in this figure. And the sum total, you can end up with either an asymmetric non-ideality, or something as extreme as this sort of W shape, which means that you've got a miscibility gap. There's limited solution in each of the end member phases, and in between there's a field where you have two phases. Miscibility gaps like this do occur in plenty of real, important mantle phases like pyroxenes, the silicate liquids, as we see, spinel, garnet. We do need to take account of this non-ideality. You may also have ordering within a given phase, like spinel, and you may have speciation where the same chemical component could take a number of forms. For example, in a liquid, an obvious one is iron, like is it ferric or ferrous, and so on. Often, this excess free energy function here is taken to be symmetric and essentially a parabola. So that can be expressed in terms of an interaction parameter W, which may also be a function of P and T. All right, so there are two basic computational strategies for solving that condition that all the chemical potentials must be equal for a given component. You either solve lots of equations like that, or you do a constrained minimization of this potential function, which is a combination of all those each of the free energy surfaces of the stable phases. There's broadly two, so there's amongst available models, there's two approaches like this. It's important that you use the n-member properties, the thermodynamic database, as it's known, that goes with the model that you're going to use. And each of these models have different interfaces that lend themselves to different physical applications. So, at least as far as igneous processes go, we have like models that are based on the work of Mark Yorso and co-workers, and that actually is underlain by the thermodynamic database of Berman. So it's Berman, Yorso and co-workers, and then Tim Holland, Roger Powell, and their co-workers, so this the models of Holland and Powell are encapsulated in the ThermoCalc software, and now include a Mantle melting model based from calibration of the KLB1 composition, Lutz-like composition, melting experiments, and then the Berman and Yorso-based models are available in a bunch of interfaces, including a graphical user interface, which these days is called pMELTS, the latest version of it. There's also MELTS Excel, phase plot, some of it. And then there's Alpha MELTS, that's Paul and my text-based version of the code. And then there's front ends like PurpleX and Theriac Domino, which allow you to choose between models from these. But basically, the short story is, don't use these with any of the melting models, because the solid solutions that are available in these models do not match the melting model. But they can be useful for if you're interested in producing a phase. A phase diagram lookup table fixed type approach for integrating with the dynamic codes. And I'll show this example in a second. Okay. The liquid models tend to use mineral-like n-members for the species in the liquid, which are based off the corresponding solids and fit by fitting fusion curves and so on. These melting models are always complicated by the highly non-ideal behavior of the silicate melts. And there's different approaches to how you deal with that. But essentially, you usually end up slightly abandoning the solid-based liquid n-members with what in ThermoCalc speak is known as a DQF, which is basically in order to model highly asymmetric behavior. This is the excess free energy. You can do that by a simple symmetric model, say, and then a linear offset, an offset of the n-member properties, and that's one. That's included in this Jennings and Holland melting model.
What does DQF stand for?
Darken's quadratic. Oh, well, yeah,
you said it right.
Yeah, Darken's quadratic formalism.
Just
but
a quadratic model, something that is more complicated.
Yeah.
Right, I'm
Yeah.
sorry. Okay.
Yeah, but actually, as you'll see, so it's called that in the thermocalc literature. It is used in rhyolite melts, pMELTS, and all these other things. It's just not given that name. Okay. So yeah, this is using perplex. Ollie did this figure for the same bulk composition as in thermocalc. And oh yeah, I meant to say actually, it's a mess, but it's not as much of a mess as it was before he fixed a lot of stuff. So it's a mess. Yes, there are a lot of artifacts because of the way that perplex, not thermocalc, but that perplex digitizes the free energy surface. But on the other hand, there are some pros. It's something that can be generated in a semi-automatic way if you, again, if you're trying to incorporate, we're trying to encourage people to incorporate some thermodynamics in their models. So,
Well, what does the black mean? When it's showing these big
that's
black
I
spots?
guess it's the. Yeah, it's not black on this.
Oh, it's just.
It's just it is black on. It's just a particular assemblage, and unfortunately,
right,
it's
it's
obscuring
just a
the.
assemblage.
Yeah,
Okay,
it's not. It's
so
not that
we
you couldn't calculate it. It's just that
It's
the
not a failure.
yeah. All right. So yeah, perplex is a sort of rather messy kind of in this case implementation of the idea of solving a set of linear, non-linear equations that for the equality of the chemical potentials. This is the other approach, the MELTS version of it, where you minimize the Gogol if it's a constant pressure temperature bulk composition, then it gives free energy. But you can, as mentioned before, you can do the same method for other thermodynamic potentials. So MELTS takes a local approximation Taylor expansion of the free energy surface at the current bulk composition, and then does and it's able to do this because there are analytical derivatives of the gap free energy parameterization coded in, and then there's a quadratic search in the direction of the null space of the bulk composition constraints. So essentially you take the constraints, find the eigenvectors, and then vary the null ones vary everything you can vary without disobeying the bulk composition constraints. And so this was just to show that so it does that does this for what may actually be a metastable phase assemblage, and then finds a minimum. This was just to show the ones that are highlighted in yellow are the thermodynamic potentials that we spoke about earlier for conditions of relevance to geological, well, in particular igneous conditions. You can also, I won't dwell on this. There's some other algorithmic details. Okay. MELTS performs this quadratically convergent minimization of a possibly metastable equilibrium. It projects constraints, as I just said, things like bulk composition, oxygen for gas, chemical potential of oxygen actually, total entropy if it's an isentropic, for example, calculation, using single value analysis. After it's found a minimum, it then tests for phase saturation and exhaustion or exhaustion, as I put. And since 2014, the rhyolite melts graph abuser interface and other interfaces I mentioned a little while ago have included some improved algorithms for testing phase saturation, which work much better for all those phases that have ordering, like spinel and pyroxene and things. So you repeat this, and because you're talking about very small energy differences, it used to be that it was quite easy to get the wrong phase in. Now it's actually quite reliable and has been thoroughly tested. And so by sort of going around in a loop between these different stages for different phase temperatures, you can eventually achieve a global minimum. And again, if you're talking about an igneous process where it's quite likely that you're alternating between a closed and open system behavior, and you want to be able to always move back towards equilibrium without, under new conditions, this actually can make it, it's very suitable for the kind of applications that it's applied to. And here is a more formal, like this is just a binary version of what I showed earlier. That's the affinity. It's the distance in energy units between the two tangent planes.
So when
Okay.
you say, sorry,
Yeah.
when you say repeat until a global minimum, have you guaranteed that you found the global minimum, or?
It's not tested numerically, if that's what you. I mean, each minimum is tested. Is numerical, and then you try each combination of adding and losing phases. Since there's the as I said before 2014, it was relatively easy, for example, to get the wrong pyroxene in. And then, yes, there was no way, when you got to the end, it didn't know, pMELTS didn't know it was in the wrong minimum, okay? It didn't know it was in the local minimum. And it would become clear a little further down the calculation when suddenly the right, well, actually, sometimes it's path dependent, and so you might never get the right thing in. Sometimes it became clear because suddenly a phase would come in, and lots of it all at once. Since Mark implemented these new algorithms for the detection of phase saturation, I've yet to, and I've tested them not in that context, but in a slightly different context, I've yet to see it bring in the wrong phase. So, although it's not, like I say, not a numerical test, as in the sort of sense of convergence that you're probably used to, it's like I said, I haven't yet, I haven't. And one of the things I'll actually mention later is often when people calibrate thermodynamic models, they actually calibrate it in terms of energy residuals. And one of the things that I'd like to do, and it would be a good test for this, is to try and do a sort of Monte Carlo type forward models and test. That would be a way of testing. Okay. Well, that was long. Okay. So just very briefly, then, the family of pMELTS models. pMELTS was the original in Gurso and Sack 1995. Was the original model. It uses, like I said, thermodynamic end-member properties from Berman and its own liquid ones based on Berman's solids. These oxides, it has solid models that have sophisticated ordering properties, and uses a symmetric, so a regular solution model, which is where those interaction parameters W's are it's symmetric and they don't vary with pressure and temperature. They're constant. And they didn't adjust the end members in the way that the DQF sort of way. They were lucky, or that a lot of the complexity that occurs if you try to model a high dimensional system, like all the way, the whole composition space right out to the end members, that would be incredibly complex and basically impossible to do. There isn't the data to calibrate it. But they were sort of lucky that the bit in the middle, sort of, at least in terms of composition and the shape of the solidus, we'll come to that in a second, worked out quite well. There is a temperature offset. There were some composition offsets as well. Rhyolite melts, I'm not going chronologically, Rhyolite melts is in 2012, and that's essentially another one of these DQF-like adjustments. Basically, the very silica-rich compositions of the comes off, but this is not from Rhyolite melts. It's just this is four-strikes olivine liquid composition, quartz liquid composition. It's just here's one of these huge miscibility graphs, and that highly non-ideal behaviour was not captured in melts, and because it's when you're doing a thermodynamic minimization, it's the energy differences that are key. They were able to apply the DQF to the solid phases and not muck up the melts calibration previously, and then preserve the granite minimum, and except that it breaks down when we had the new fluid model, when they added the new fluid model, and so basically Rhyolite melts replaces melts for all compositions, including like the salted ones and things. And then more recently they've added a mixed fluid model to Rhyolite melts, calibrated on a wide range of data. I'm just going to skip over very quickly. A wide range of bulk compositions. So sorry, this was for pure water fluid. So water saturated solubility experiments, pure carbon dioxide solubility, and then mixed fluid experiments, and then a wide range of bulk compositions of the silicate.
What's being plotted?
Oh, this is like a standard task plot. Sodium plus potassium, silicon, and there's each of these like fields has its name. Has a name, like it's a classification plot for basalt and basanite and.
So
and
the little symbols occur at some part of.
So each of these is each of these is a plot of the bulk composition for an experiment that someone has. In practice, because most of these are solubility in silicate melts, that's also the liquid composition. Except generally that wouldn't be true in a petrological experiment, but for most of these it is. The model does a good job of recovering the solubility for carbon dioxide at pressures up to 3 GPa, I think. Oh, it's back further. Yeah, 3 GPa, or 2 really. It's internally consistent, it adopts and is internally consistent with the mixed fluid model of Duran 2014. And it also does a good job of recovering the mixed fluid data, which and the change in with pressure. This is like from 100 bars to 500 bars, these curves.
So usually when you have things like, I remember like volatile calc and so on, like when you're at the low water side, it kind of flattens off.
Yeah.
Just sort of, why does this not flatten off in the same way?
So that that's just because that's the way that people tend to parameterize it, and I forget who it was, but there was somebody who predicted that actually it should tail down. This was not an expected result when Mark started doing this, but it is actually thermodynamically consistent. And I'll have to ask Mark who it was, but yes, this is consistent, and as you can see, internally consistent and well within the uncertainty of the of the data, but like you say, if you were just going to do a direct parameterization, you wouldn't think of just fit the data with a polynomial or something. You wouldn't be doing that. But that falls out of the way the mixing model is formulated. pMELTS was a 2001 update to MELTS for higher pressures. So whereas MELTS was only really good up to 2 GPa and really only up to 1 GPa as far as the fluid, the water, which in that case was just water. MELTS uses a Birch-Mernon equation of state for the liquid, so it can go up to higher pressures. It's still not as good actually at the lowest pressures. It doesn't have quite so many. Not all of the components that were in MELTS are actually in pMELTS. And yes, and in particular, it doesn't change the solid solution models. And those solid solution models, the equation of state, the model of how volume depends on pressure and temperature and composition, doesn't extend very well to high pressures. So one consequence of that is that the solids tend to turn over a little bit like this, which I think in MELTS, what happened was the equation of state for both the liquid and the solids was wrong, but it was wrong in the same way, and so it kind of cancelled out, and you got a solidus that did what it should do, and kind of even if it wasn't in the right place in temperature, it was the right shape. But now pMELTS doesn't extend to high pressures quite so well. xMELTS is very much still under development, but that will go both to much higher pressures, this way, sorry, to the base of the transition zone. It's X to denote a speciation model, in particular for the speciation of iron. These are potential species. It hasn't been calibrated. It's not that all of these would be in the final model. It's just that these species that would be tested if and when we get to that stage. And it's also X for extreme conditions, much higher pressures. And yeah, we were working on putting chrome into garnet, which is one of the major problems with MELTS and pMELTS, and other improvements to the solid solutions. pH MELTS, that's Paul's model, is based on pMELTS, something very similar, and it allows water to partition as well as into the major element, all the major like liquid and hydrous phases, the sort of thermodynamic part of the program of the algorithm. It can also partition it as a trace species into anomaly and hydrous minerals. Okay. And then just very quickly, I mentioned alpha MELTS. That's our sort of text-based front end to well, pH MELTS, pMELTS, and MELTS, not Rhyolite MELTS yet. And this is just an example from a few years ago, where we coupled the pH MELTS model with a two-dimensional flow code, and because MELTS, or pH MELTS in this case, can give you so much information about the energy budget, the water and anomaly and hydrous minerals, and you can have that feedback with viscosity, with we were able to deal with the latent heat of melting, kind of in a rigorous way by modifying the advection equation. This was a text-based coupling scheme. It was a nightmare, very kludgy. It's kind of where we were at 7.5 years ago, and at the moment but we were getting sort of towards, it's in the right ballpark in terms of the chemistry, and where the fluid release, and the formation of a chloride and serpentine on the zone, in the adjacent to the mantle. At the moment, I'm completely rewriting the pMELTS code to be based on the Rhyolite-XML code, including the new Rhyolite-MELTS model, the improved algorithms for detection of phase transition, and two library versions, which, although that's not not relevant to the carbon dioxide question, it's why I'm visiting the MELTS and the Mantle program. So this is coming soon. It's a high-level. It would be kind of suitable for doing modeling from MATLAB or something like that. If you want like scripted, lib pHMELTS will be like fully threaded, and it's much lower level access, and I can hope to get some kind of. I hope that talking to people here will give me some guidance about how to write it and what to put in. Okay, I'm going to try to zip through this bit. Yeah, so just a little background, how do you calibrate thermodynamic models? You usually calibrate all the end member properties first. If you just tabulated the available data, it would not be internally consistent, which is to say it would not predict the reactions between the pure phase end members to land in the right places. So instead you actually calibrate that. And then build the solid solution and liquid models on that. This isn't. So when you start to actually fit the solution models, what starts to become difficult is how to visualize what the form of the model should be. And so this is a relatively simple example because it's only dealing with volume. You can calibrate that without having to worry about other phases, and it's not showing very well, but this is actually our model. There's 5 dependent end members, 3 dependent ones. There's also ordering amongst most of those end members. This is the model with the effective ordering and the ideal contribution subtracted, and so you can, this is the dependent end member picromet. And you can see that it does a pretty good job. This is Bray et al.'s model for their data, which is the diamond. So it's like specific to their experiments, and although it does slightly better job of returning their experimental data, it doesn't capture the rest of the spinel data that's available, and it also illustrates what I was trying to. Here we've had to subtract the end members of this. So this is subtracting their end members. This is subtracting our end members, ideal and ordering contributions, which goes back to this point that you can only use the model. It's all or nothing. You have to use the thermodynamic database that goes with the solid solution models, that goes with the liquid models, and not try to mix them. And this. So for this particular model, and I'm sorry that you can't really see the surfaces, it was quite easy to see what a good functional form would be. You can plot, but when you start to get into solid solution models with like 9 independent end members, which the XMELT model in Garnet will eventually have, you might be talking about 40 dependent end members. You can't do it that way anymore. It's true, only 6 of them have data. But you can't also just say, okay, I'm going to set all these parameters to 0, because the lack of data might be because nobody's gone and measured it, but it also just might be because there's miscibility. It's non-ideal, so there aren't any stable garnets in that region to measure, for example. Okay, so there's a couple of ways that we can approach this. One is to use essentially the same trick as I was talking about before, where you project the constraints now and minimize, vary those the parameters that fit both the independent end member data and the dependent end member data. That's a single value analysis algorithm. Or to use a fully Bayesian approach in which you minimize the the residual that's between the model and the data, but also like chi-squared like penalty terms for the uncertainties in the parameters as well as in the data. This is supposed to be down here. Yeah, if you use that kind of approach, you get a so one thing I should say that the parameters are highly correlated in these types of models, and so this gives you a way of getting all the correlations and uncertainties in the final parameters, which can then be fed into the next step of the model, so you can build it up. When we were doing this Bayesian approach, we used actually, because people tend not to report uncertainties or they tend to underestimate their uncertainties, we were able to use the intrinsic scatter in the data to get a better estimate of the uncertainty and weight the data that way. And this is where we were getting the kind of fitting different binaries to get initial estimates for the interaction parameters and some feeling, and then we were able to plug in like a combination of these. This is, each one of these is one binary, and this is sort of consistent with the general idea that the interaction parameters are usually not very negative. You kind of expect them to be, they could be positive, but not too positive, and you expect them to be less negative. This is the results of that. So the solid line is the Bayesian model with the 2 sigma, I think it was, envelope. The dashed line is the singular value analysis plus me, plus us manually filtering the data out and a lot of the noise, and making decisions about which parameters we would fix to zero, fix to zero. And as you can see, like sometimes the parameters are actually quite well resolved, even when there's no data around. But this is still much more simple than trying to do the full solution models, where you're actually dependent on other types of data and other M members, other phases, sorry. But broadly speaking, for liquids, you use equality constraints, or in general, people have used equality constraints between the phases that are at equilibrium in a given hydrological experiment, and phase absent. You can optionally phase absent constraints, where you penalise if a phase appears to be stable when it shouldn't be. Eventually, Mark hopes to have a scheme where you would be able, instead of like everything being built on things that like thermodynamic databases that were made in the late 80s and then fixed, that it would be much more flexible. But we're not going to try to, that's going to take a long time to implement, and so in the meantime we're going to use a simpler model for this. So yeah, the fate of carbon in the mantle is a subject of current interest, and deeper in the mantle, where carbon should be reduced, you don't expect it to really influence melting very much. But in the oxidized upper mantle, but still deeper than where hydrous or anhydrous melting would occur, we expect the first melts to be carbonatite, like where carbonatite is a melt that's more than 50% carbonate minerals. Experiments show that as you increase the carbon dioxide content of the experiment, that you go from carbonated silicate melts up into carbonatite melts at the highest weight percent carbon dioxide. But at low pressures, you tend to get like two phases, like so either a silicate liquid and a carbonatite liquid, or unmixing. So a single phase at high temperatures, and then as it cools, it mixes into carbonatite in the silicate liquid, glass. And somewhere there's, you know, in pressure composition space, that you switch between the behavior of having a carbonate liquid, a single carbonatite liquid, or a carbonated silicate liquid, or two coexisting. I'm showing this data, which is significant. This is for the rhyolite composition, carbon dioxide solubility for experiments by Megan Duncan. This is significant because it was not included in the calibration for the rhyolite melts plus fluid model, and yet the model clearly reproduces the data virtually within uncertainty. These are Paul's calculations using the rhyolite melts plus, well, mixed fluid, but just the carbon dioxide part of it model, for a bulk composition that it really shouldn't be able to deal with, and the pressures that it shouldn't really be able to deal with. So the liquid, the fluid model is good up to 10 GPa, but the liquid model for rhyolite melts, remember, is only good up to about 2 GPa. So this is temperature. This is the melt fraction, well, not melt fraction, but mass of melt out of 100 grams. So, and you get this long tail where you get a small amount of very carbonate-rich melt, and then sudden increase in melt productivity with well, it's not really with temperature, and then this is completely molten. And what you find is that these are the silicate melts. These are carbonatite melts. Here's the carbonatite melts. These ones, these. It's not very well. It's a little small, but essentially, rhyolite melts plus the fluid model is capturing that behavior that at low pressures you get two melts, a coexisting carbonatite and silicate melt, and then at high pressures you get a single carbonated silicate melt. So even though no two liquid constraints were included in the calibration of rhyolite melts with this fluid, there's nothing in the calibration that from experiments where they measured carbonatite melts. It gives a qualitatively correct the phase relations, and we hope to, by switching to the liquid model that's suitable for higher pressures, we hope that we should be able to improve quantitatively. This is just a projection of both the experiment results, and here's the calculations. Okay, then fine. So as I mentioned at the start, Ollie came on board with this project really quite recently, so it's very much work in progress. It's just getting going again. This is what we have so far. We have a almost completed live alpha melts library that is suitable for that we'll be accessing from a calibration code, which is somewhat but not completely written. I mean, the calibration code is somewhat but not completely written. This library, I've implemented the pMELTS plus CO2 speciation in the melt, taking the rhyolite melts parameters provisionally. So in rhyolite melts, the speciation reaction is this. There's three possible. There's calcium silicate, calcium carbonate, and a carbon dioxide species in the melt. Because the silica liquid M member in pMELTS is different, we end up with this reaction, which doesn't look very different here, but in terms of code, it makes quite a lot of difference in different places. And we also have a database which we call LEPCORN. It's based on the Library of Experimental Phase Relations, otherwise known as LEPR, which is publicly available. Our local CALTECH version of this adds the volume and site occupancy data that we use for what I showed earlier. It adds finer grained metadata, which is what we use for the Bayesian approach. So instead of just recording this experiment, we did some analyses by XLE, we did some by microprobe, where it's on a measurement by measurement basis. This composition was constrained. Comes from a microprobe analysis. This site occupancy comes from a combination of XRD and so on. So that we have a much better way to think about weighting the data correctly. And it has a number of sort of smaller things that we can add after we transfer data from here, like being able to distinguish between different carbonate phases. In LEPR, everything is just carbonate. Whereas in experiments, you might have carbonate, you might have dolomite, you might have magnesite, especially when you're talking about more mantle related bulk compositions. And so this database now has all of the data that were used in the Rayleigh melts and plus fluid calibration, many of which are still relevant for the pMELTS plus CO2 calibration. We've entered most of the available, not all, but most of the available data just for normally anhydrous carbon dioxide solubility and so on. And we can interrogate this data set. So initially we're just going to calibrate for pure CO2, not the not a mixed fluids, because the equation of state for water that's used in pMELTS is not, it's not Duan, it's Pitcher and Sterner. Eventually we hope to actually do a full recalibration so that everything is consistent. Because, especially in, it's quite difficult to quench and analyze carbonatites, so that means that there's a lot of experiments where carbonatite has been, is there, but it doesn't, we don't have the actual composition, so we can use, just like before I was talking about phase absent constraints, we can use phase present constraints, but without the actual compositions. So carbonatite, phase present, fluid present, but not analyzed. When we eventually get to mixed fluids, that's more appropriate at the moment. Any two liquid experiments like the ones we were showing before, the constraints from that, and carbonate bearing experiments. So all of these constraints we can actually use in a way that the Rayleigh melts plus fluid calibration didn't need to use really. Okay, so the blacks. This just shows you the distribution of the data. This is the Duncan and Dasgupta data, which, like I say, wasn't included. The open circles, the black ones, they're from the Rayleigh melts plus fluid calibration. This is just for pure CO2. The red ones are ones that are in their database but weren't actually calibrated. They're just from comparison. And the mustard kind of ones are the new data that we've entered. You can see that you get the same. This is the same color scheme. This is carbon dioxide in the melt, and silica in the melt. So you can see that we get the same sort of range that I was in the figure earlier, going from through carbonated silicates right over to carbonatite. There's this gap that in the other plots, all the data in here was from synthetic systems, which melts like low variance systems, which we don't try to use in in the sort of MELTS world, because like I was saying, going from a sort of, you have to introduce so much complexity to try and model the synthetic low variance systems and the natural systems simultaneously, that MELTS doesn't try to do that. But anyway, there's some components of it. This is carbon dioxide in the MELTS, the glasses, and this is sodium in the MELTS. And you can see that, and actually some of these are more than likely underestimate the sodium content for experimental reasons. So you can see that for these higher pressure experiments, we may have to try a sodium carbonate species in the liquid. I mean, initially we'll just try the same 3 species that I showed before, but that's something that might have to happen, either instead of or as well as the calcium carbonate species. It wasn't justified for the lower pressure. And so, yeah, this is really just like the conclusions and kind of where we're going with this. So initially we'll start with the pure CO2. Eventually we hope to adopt the Duan equation of state for the liquid, for water as well, and the mixed fluid model. But that would require a recalibration of pMELTS. So a sort of not as extensive a recalibration as xMELTS will eventually be, but something that would be an improvement on the current pMELTS, as well as maybe needing a sodium carbonate species in the liquid. We might also use a test whether you need a molecular water species. Currently, all of the MELTS models, water is only incorporated in the liquid as hydroxyl, which we know not to be the case in real life. But again, up till now, a molecular water species in the MELT wasn't justified by the data, or at least according to Mark. So that that's something that we will start looking at after we see what we learn from trying just pure CO2. While we're at it, if we're going to recalibrate pMELTS, then we might as well try and address some of the things that frequent criticisms of MELTS and pMELTS, like the solidus that turns over, and the temperature offset. I mean, I mentioned that I think that some of that temperature offset in the solidus and liquidus, sorry, in the anhydrous solidus and the solidus and liquidus, it kind of gets stretched out. Is to do with always calibrating or always minimizing energy residuals rather than like the separate like pressure, temperature, composition. We might consider looking at some of those issues. We might consider calibrating oxygen fugacity, because at the moment there's an inconsistency in the MELTS model between the Crescent-Carmichael model that it uses, which is not actually self-consistent with the thermodynamics of the liquid model. But again, we would be doing something a lot simpler than the old xMELTS model. And also, to try to extend the equation state of the solid phases to a bit higher pressures. So so that should help with this, the solidus rolling over like that. When we were doing those subduction zone simulations, we basically did this. We used Berman in the zone where liquid has the pMELTS liquid had been calibrated, and then we extended it with the Birch-Mernon equation at high pressures where there wasn't any liquid, so we weren't, but we needed the physical properties of the mantle to feed back into the convection flow code. So so that's a possibility, that we might be able to take pMELTS a little bit more P Yeah, and also possibly do some, inclusion of some more M members. Chrome and garnet would be the #1 priority in the solid solutions, without going to a full like 9 M member garnet and all that. So that's it really. That's where it is at the moment, where we're trying to get.
Thank you very much, Paula. Do we have any questions?
Are you going to put trace element partitioning into the carbonatite part of it? Because I was thinking about things like, people are keen on carbon niobium ratios or carbon barium ratios.
Yeah.
And if they thought that making carbonatite could do something quite bad, well, could fractionate carbon from niobium, carbon from other trace elements that people like to have sort of coupled as geochemical twins. So I wondered if you were going to include something like that in the models.
Yes, so one of the things I'm doing with this rewrite is completely rewriting the trace element engine, which up to now has just been this sort of tack on. I mean, it's only slight, other than when it's being used for pMELTS, it's not really that different to doing a MELTS calculation and then back calculating all the trace elements in Excel or some other script. So yes, so we're completely overhauling that for many reasons. And one of the things I'm doing is working with John Blundy to extend the lattice strain model so that you would be able to do a lot more combinations of phases and species, trace element species. And another thing that we're doing is the ability to, this is with Eric Harry, to eventually to be able to slot in your own, like at the moment you can define your own constant partition coefficients. You have a tiny bit of control about the lattice strain model, and that's it. You can't do anything else. There's no in between more empirical parameterization. So eventually you would be able to slot in your own functions for the partitioning of a particular mineral, and so you could have you can add a bit that tests whether this is a carbonatite or whether this is a silicate liquid, and then.
But in that case, will the liquid composition may, because usually the lattice strain model, the strains is in the crystal and the solid phases, but in this case there will be such variation. I mean, the liquid structure is going to be so different that that's going to start playing a role in the partitioning.
Right. So you would be able to have an empirical model or something that's based on the lattice strain models. I mean, there's some hybrid models out there already, like Sarah Miller's work, where she used the lattice strain model, but she had some terms that came from the liquid composition. So, if you coded up in, it's likely to be either like MATLAB or Python, but that it's the easiest to slot into the library functions. But we'll see. That I know how to do it in the others. I don't know how to. It would get a little trickier for the others, but it's possible. Anyway, if you have your function, you can decide, I'm going to use the lattice strain model or not. I'm going to take what the terms from the lattice strain model and add some stuff, or I'm just going to, I've got too much carbonate around, I'm just going to ignore the lattice strain model and use other. So I mean, I don't off the top of my head know. What data you would use for carbonatite trace element partitioning, but someone who is actually that's their thing. They can and also originally I kind of thought I would have maybe a default set of partition coefficients or partitioning behavior, but because these compilations tend to be not quite complete, and so you end up with some things that just end up being perfectly incompatible without it really being that obvious. I think it's actually better just to have everything is perfectly that you have to define. You have to say which partition coefficients you want, basically. I don't know whether so there's TraceD's database, which is basically LEPA plus the Roger Nielsen and Markios's. Well, I don't know whether they have any really extreme compositions like that, but if they do, another thing that we will have is the ability to download XML files from that database and stick them in. So you could say, if this looks like a carbonatite, please use this instead of that. But that's all a little way down the road. Yeah.
Any further questions?
You sounded surprised that sodium carbonate might be important. Yeah,
Oh,
it's
no,
erupted, isn't it? So
No, I
don't
didn't.
know.
No, we're not. It's not that we're surprised. It's actually that we think that we are almost certainly going to have to do that. The point was that when Mark was looking at the was doing the pMELTS plus fluid calibration, where he was looking at rhyolites mostly, but not exclusively. He certainly wasn't looking at carbonatites. He couldn't justify he did try a sodium carbonate species in the liquid. He just couldn't justify it with the data, and so he just probably folded in everything into the calcium carbonate species. We fully expect that we will have to use the sodium carbonate species, like I say, either instead or as well as. It's just that at the moment we have the calcium carbonate model, the model using calcium carbonate, coded up, and so that's a good place to start, and then we see whether what happens and what the residuals look like, and try and then code up the sodium carbonate. But no, we're not surprised. It's just like we haven't implemented it yet.
What's the spinel to garnet transition depth in
In what is it, or what is it?
Yeah, what is it? Just what is it?
It's a particular pressure, isn't it?
Yeah.
Well, I mean, you expect it to be not uniform, but not as it's very smeared out in March because of the. I mean, because of the. There's no chrome going into the garnet, so we basically always have a bit of spinel, and that's why. Even if we don't do the full extended garnet and pyroxene solid solution models that will eventually go into pMELTS, just putting chrome in garnet would make a big difference. And then hopefully, originally the spinel garnet transition was in about the right place, and then it turned out that there had been a mistake in the coding of the activity coefficients in the garnet. That there was a mistake in the paper, the Berman paper, and that got into the code, and that was in the code when the calibration was done. So when that was corrected, which gives you better garnet compositions, the spinel garnet transition ended up somewhere incorrect because it was no longer consistent with when that had been calibrated. So that's another. I mean, that's another reason for a mini recalibrate or a recalibration of pMELTS, is because we can now have that corrected garnet model. We've had some success putting just a simple manganese member into garnet as well for some rhyolites that we've been studying. So yeah, it would be quite easy just, and then hopefully, I mean, I don't know that. I think it's like it was about 2 GPa, and then after they corrected the garnet, it went right down to like 1 or something, and it's really like, yeah, it's just not right. But yeah, that would be a good thing to fix as well.
Okay, I think we should leave it there. We just thank Paula once again. Thank you very much.